So I want to tell you a bit about Monte Carlo methods, and I'll start with a very general introduction about the method. Today I won't be discussing how Monte Carlo methods can be used to solve quantum impurity problems within DMFT. This is something that I will be addressing tomorrow. Today is really the basics about Monte Carlo. I'll be illustrating it on classical examples, mainly on the Ising model. And I basically want to get to the Metropolis-Hastings algorithm. That's the goal for today. I suppose that for many of you, this is material that you already know, but I think it's good that we start off with the same base. So I have a bunch of slides, and you can have access to those slides if you go to the Tricks Summer School website, and Niels has just added a bunch of links. So one of them is a link to the slides. And as you will see, my slides are based on a bunch of notebooks. So all the material that you see in the slides are actually notebooks. And you can find all the snippets of code that generate the figures that I'll be showing. So if you want to play with the parameters, redo some of those simulations, you can actually go and either download those notebooks from the second link here, or there's a binder link where you can directly interact with the notebooks, which is this first link here. Okay? So don't hesitate, especially if you know the material, to go to those notebooks and have a look at them and play with them if you like. Great. Very good. So those notebooks are basically organized a bit like the outline of the lecture. So I'll be first introducing Monte Carlo, compare how Monte Carlo methods can be used to compute integral and how this compares with Newton quotas quadratures, and then I'll discuss different ways to sample different probability distributions. So it's organized like this, and if you go and have a look at the notebooks, they're organized exactly in the same way, so the different chapters of the outline are those different notebooks here, and you can find the content of the slides there. All right. Please interrupt me at any time if you have questions. This should be fairly basic material, but it's good that you know it, so make sure that if you have questions, you stop me. Very good. So maybe just to start, the motivation for Monte Carlo method, there are stochastic methods, and they're used in situations where we're dealing with systems that have many, many degrees or internal degrees of freedom, which we typically meet in condensed matter physics. And to compute physical observables, if you think, for example, about computing a partition function, what we need to do is really sum over all the possible configurations that the system can have, and this very quickly becomes very difficult. So even if you take a simple two-dimensional Ising model or an Ising model with n spins, well, the number of terms that you need to sum to actually compute the partition function is, well, 2 to the power n, and this very, very quickly becomes impossible to do. Even just challenging 20 spins is something that becomes very, very difficult, and we're very far from a thermodynamic system. So this is where Monte Carlo methods can be useful. They allow to approach these problems without having to actually really do the complete sum over all configurations. So that's the motivation. Maybe just one slide about a bit the story of Monte Carlo. So Monte Carlo methods have really grown at the same time as modern computers. And maybe the two fathers of Monte Carlo methods are Stanislav Ulam and John von Neumann. I'm pretty sure you know von Neumann. Maybe not all of you know Stanislav Ulam. Both of so he's a Polish-American mathematician and physicist. They both met during the Second World War. They were participating in the Manhattan Project in Los Alamos. And after the war, Stanislav Ulam went back to California to teach to the University of Southern California. And in '46, he got sick. He got a brain infection and had to spend quite a bit of time in the hospital. And to kill time, he played the solitaire card game. And as a mathematician, he was interested in knowing, okay, what are my odds? What are the chances that I have to win at the solitaire? And as you can figure, this is a very difficult combinatorial problem. So he had the idea to just play it 100 times and say, okay, if I do this 100 times, how many times have I been winning? How many times have I been losing? And out of these statistics, can I get an idea of what are my chances? So he went back to Los Alamos and talked with von Neumann about this idea. And this was exactly the moment when the first computers, especially the ENIAC programmable computer, was born. It was in 45. And they immediately had the idea to use these ideas of sampling processes to do and study physics, and especially the neutron diffusion problem. And by 48, they had the first code implementing these ideas on the ENIAC computer, and I think this was really the birth of Monte Carlo, and the Metropolis method is just a couple of years later, end of the 40s. Okay, so what's the spirit? How can we use Monte Carlo? So the spirit of Monte Carlo is a very physical principle, is the idea that in order to understand the physics of the system, I don't necessarily need to actually sample and go through all possible configurations that the system will go through, but what I really need to do is try to find and investigate what are typical and what are meaningful configurations. And actually, this is also most likely what happens in true nature. In true nature, systems don't take all the possible configurations they can go to. They actually really go in the most likely ones, and this is the spirit of the stochastic method. Go to the configurations of a system which are the most useful ones and try to extract information from it. So this is used in all sorts of different contexts, and the context that I want to discuss here is how to use Monte Carlo to do integration, how to do sums over all possible configurations, how to integrate using stochastic methods. So let me illustrate this on a very simple problem, which is how can I compute pi? By throwing pebbles. So imagine you have a pond, which is this circle here, radius 1, and I put this pond inside a square of size 2. Clearly, if I want to compute pi, I can obtain this from taking the ratio between the area of the circle and the area of the square and multiply by the area of the square, which is 4, right? This is this formula here. So if I find a way to stochastically evaluate this fraction, the ratio of the pond size with respect to the square, well, I can get an estimate of pi. Okay? So for this, I need to be able to throw many pebbles in an unbiased, uniform way in the square. It's a bit cumbersome to do if you do it yourself, but we have computers to do this. So that's a small snippet of code that does exactly this. It throws 2 to the 12 pebbles. It's not something you want to do yourself. It throws them uniformly on the square, and you get all these purple dots. And this little snippet of code counts how many of those pebbles fell inside the circle with respect to the total. In this case, I threw 4,096 pebbles, and about 3,200 fell inside the circle. So if I take the ratio and multiply by 4, I get an estimate for pi, which is 2.11. Not great, but that's a start. It's not that far. So I've basically been trading an integration problem, which would be to integrate the area of the circle into, well, a probability problem, which is to compute this ratio. So let me try to make this slightly more formal, maybe mathematically, and describe this throwing of a pebble by a random variable. So the nth throw of a pebble is this random variable xn. It can take two values, either value 4, and this happens with probably pi over 4. This is falling in the circle. And it takes value 0 with the remaining probability. Okay? So clearly the average of this random variable, well, is pi over 4. This probability times 4 plus 0 times the remaining probability, that's pi. So you see I've traded this integration problem for the problem of computing an average. Okay? So this is how stochastic methods can be used to try to compute integrals. Okay? So is there a strategy to generalize these ideas? So this is a circle computing an area. Can I do this to integrate functions and multivariable functions? So this will be the topic of the lecture. And also, how does this compare with more standard methods of computing integrals? Right? Very good. Any questions so far? I think this is, yeah?
For the circle example, if we had like a regular array of points, that would not be probabilistic, so it's easier to integrating it, and you're saying it's maybe more efficient to have a more probabilistic interpretation with these random dots as opposed to a regular grid.
Yes, so I'll come back to that. I mean, actually in 2 dimensions like this problem here, you actually would be much better off taking regular points and using clever Newton-Cotes quadrature rules, which I'll express right now. So actually it's as the dimension of the function that you're trying to integrate becomes large that those methods start to be useful. In that very specific example, you'd actually be better off choosing regular grid points. Okay. Here it's more a question of showing the principle, but I'll come exactly to that question right now. Any other question? So yeah, let me actually exactly do what you're suggesting here. So imagine I want to integrate a function. This is an example here, using my standard Newton-Cotes rule. So I take an interval, and the standard approach is to divide this on a regular grid of width delta. And then there's different ways and different integration rules that you probably know fairly well. The most common one is just the rectangular one, in which I just take the value and multiply by the width. And this is a method that is said to be of order 1 over n, meaning that the error I'm making typically on the integral scales as 1 over the number of discretization points. You can go trapezoidal. The formula now involves more evaluations, but the rule now goes as 1 over n squared. You can go Simpson, 1 over n4, and so on and so forth. Okay? So there's in the notebook and here a little example of actually using these quadrature rules to compute this simple integral of this exponential function here between 0 and 1/2. And you'll observe that if you look at the error you're making as a function of the number of points of divisions you use on the interval, they indeed decrease as 1 over n, 1 over n squared, 1 over n4. Okay? So this is actually quite and very efficient for one-dimensional functions. Okay? But the difficulty comes when you start increasing the number of variables that you integrate over or the dimension of your space. So how does that work? So imagine I have a method like the Simpson method that is of order k. Okay? For the Simpson method, the order is 4. Okay? In one dimension, this means my error goes as 1 over n to the k to the 4. Okay? But imagine I'm in d dimension. If I throw a total of n points, well, it means that in a single direction, in a single dimension, I only have square roots, d's square root of n points. So m to the d is n. Okay? So my error typically scales as what happens in that one dimension, right? It's not 1 over n, it's really 1 over this m here. And so the error now goes as 1 over n k, which is the order of my approximation, divided by the dimension. As this dimension grows large, and when we talk large in typical systems that we're looking at in condensed matter, this can be hundreds. Well, you see that no matter how large you take your method here, you will never, this will become very, very bad very, very quickly. So this is where stochastic methods will become useful once you reach dimensions beyond 10 or so. Stochastic methods will start to be much more useful. So how do they converge? So how do stochastic methods converge? Well, let's take our problem. Again, we had a random variable which had average value pi. Now what's the standard deviation? What's the statistical error I'm making if I make a single throw? So on a single throw, well, you just take the average of the square. This is 16 times pi over 4, that's 4 pi plus 0. So my variance is 4 pi. And my standard deviation is something like square root of 4 pi minus pi squared. Don't mind the precise number, this is big. I mean, this is almost as big as pi itself, which is not surprising. I mean, I get either 0 or 4. I cannot get a serious estimate for pi in a single throw. Okay? The point is that I will be repeating the experiment many, many times. This is the key. Okay? So in that respect, I introduce an empirical average, which is the average over many throws. So I take n throws, and I take the average of those n throws. So it's a new random variable that is the average of those n throws. Obviously, the average of this is, again, the average of the original throw, so the average is pi, so I still have an estimate for pi when it comes to the average. But now when I look at the standard deviation, and I'll let you do the math more carefully, if you take this formula and compute the standard deviation, you'll see that the standard deviation of the empirical average of your nth rows is something which goes like the standard deviation of a single row, which is this constant here, but then divided by square root of the number of throws. And this is the key. The more you will repeat your experiment, the more pebbles you throw, the better your estimate, the smallest the standard deviation, and it goes as 1 over square root of n, and this does not depend on the dimension of your problem. Okay? So this is where this is a bit stronger than the usual methods in Newton-Cotes quadratures. It does not, as your dimension increases, have a different scaling. It always goes as 1 over square root of n. All right, so that's the motivation. This is where stochastic methods are going to be useful. Any questions about this? Okay. So I'll introduce a very important concept that is called importance sampling. So let's try to be now a bit more realistic. We're not going to compute pi anymore, but let's actually try to compute an integral of some function. Okay, so I took an example here, which is some oscillating function, and it's damped by a Gaussian, okay, of width 1.5 here. Okay? So it looks like this. The actual integral of this function is something like 7.52. Doesn't really matter for the purpose of what we do. So how can I sample this integral stochastically? Well, it's quite easy. What I do is I throw random points on the interval of integration. Okay? So with a uniform distribution. So I randomly take uniform points between a and b, which are my integration limits. So formally, how can I write this? So what I want to compute is this integral, which is the integral of the function between a and b. And I'll rewrite this as an integral of f divided by pi multiplied by pi. I haven't done anything, but I've introduced pi, which is the distribution function that I want to use to throw my evaluation points. Okay? In the case of a uniform sampling, this probability distribution is just a constant. And as you see, it's normalized to 1. It takes value 1 over the length of the interval. So if I integrate this over x, this is a normalized probability distribution. So what I will be doing many, many times is when I see an integral like this, it's an integral of a probability distribution times something. Well, if I want to approximate this stochastically, what I do is I draw samples with this probability distribution, and I evaluate the average of the remaining function, which is f of x divided by pi of x in that case. So I throw n points uniformly, and I evaluate f of xi divided by pi of xi, and I do the average of this. Okay? That's how I can try to evaluate this integral. So do you think this will work? Who thinks this works? No one. This will not work. Let's say I take n very, very large. Will this in principle work at least? No. Actually, yes, in principle it works. There's nothing wrong in what I wrote here. It works, but is this efficient? So why is it not efficient?
Because we sample many points where the function is just 0.
Very good, exactly. So let me do the experiment. I throw these points. These are the red crosses here. In principle, if I do this, I will eventually get the integral, but I'm wasting a lot of energy throwing points in areas here and here where the function is basically 0. So it's not that it's not working, but I'm wasting a lot of energy doing something which doesn't help me. Okay? So what would be a better way?
Sample the points where the function is like
Exactly. It would be a much better idea to try to sample the function in places where the function has structure. Okay? So to basically go where the information is. Okay? So yes, actually I'm lucky. The formulas I wrote are quite general. Up to here, this pi of x can be anything. So instead of taking something purely uniform on a certain interval, I could actually take something different, which is more centered around the place where the function has its largest value and its more delicate structure. For example, I could take just a simple Gaussian. Okay? So that's an example. So this red thing here is a probability distribution that now samples point according to a Gaussian. We'll see later how to do this. It's not entirely trivial. But let's suppose I can do that. Well, you see, in that case, it's in a sense better because now my points are at least centered in places where the function has structure. But are those points all good? Is this going to be very good? Is there a way to be better? What's your opinion?
The Gaussian should be wider.
Yeah, you see, there's a bit of a trade-off. I mean, if I make this thing too narrow, I'll be only sampling things right in the middle of the function, and I'll lose the information on the end. If I make it too wide, I'll start sampling things that are too far. So there must be some sort of optimum. So let's look for this, and I'll parameterize this, the width of my Gaussian, with a free parameter, which is sigma, the width of my Gaussian. Okay? And again, you can go have a look at the little code. What I've been doing is I've been comparing the standard deviation of my result with respect to the exact solution for different values of sigma. If my sigma is too small, I'm sampling only the center of the function, and this generates a larger deviation, standard deviation. If the width is too large, I have the previous problem, start sampling things that are useless. And there's an optimal, which is about at 1.5. Does this ring a bell? Let's see who's been really careful. Yeah?
That was the original width of the
Exactly, good memory. My original function was basically something oscillating, but damped by an exponential, by a Gaussian, sorry, which actually had width 1.5. So it is that distribution that actually matches or fits that thing best that is the most efficient, and it's not that surprising. So the closer I am to the original function, the better my result or my standard deviation will be. So it's not that much a matter of being wrong or right. It's just that I'm more efficient, I have a better standard deviation if I actually match my function best. Okay? Great. So that's the distribution. That's what it looks like. And as you see, it quite nicely fits the function, especially it gets this decay quite nicely here. All right. So that's important sampling. Sample functions in the places where they're important. That's important sampling. So this belongs to a family of techniques that are called variance reduction techniques. Again, the goal is to try to reduce the variance. Okay? But as you see, yeah?
Am I still guaranteed to get this 1 over square root of n?
Yes.
Here?
So in all cases here, you'll get the 1 over square root of n, but the prefactor changes. So by tuning things correctly, what I get is a better prefactor, but they all go like 1 over square root of n. Yeah, very good question.
But we always need then, sometimes we don't know, also, like if this especially functions in many dimensions, how do we always need to choose this proper
Exactly. So, so this will be one of the major challenges will be indeed to find something that fits the function best. But what would be the best choice? The function itself. There's one issue with this though. Can you guess what it is? Exactly. So if I just do this, and I was trying to get as a probability distribution the function itself, I would have to normalize the probability distribution, which is normalized by the integral of the function, which is exactly what I'm looking for. Okay? So for this specific purpose, well, we'd have to think slightly differently. But you'll see in statistical physics, we actually get lucky because we get ratios, and this normalization constant will disappear. But still, the main idea is to try to sample the function directly up to a constant. Okay? And this is exactly what we'll be discussing in the Metropolis-Hastings algorithm. Okay? Very nice. So you see, the game is definitely that we need to try to sample distributions that are not necessarily just the uniform one. So we need to start from something, and so I will have to assume that I have some engine, a computer, that is able to draw uniform random numbers between 0 and 1. Okay? We can have a full lecture about how to do this in a clever way, how to be unbiased, how to eliminate autocorrelations, and so on and so forth. This is not the topic of this lecture. I just suppose that I have a good random number generator, sampling numbers between 0 and 1. And then starting from that, I want to try to draw random numbers according to a certain distribution that I choose. Okay? In the best situations, this can be done with uncorrelated samples, meaning that every new number that I will produce will be distributed according to the probability distribution that I choose, and will not have any correlation with previous points that I have been throwing. This is not something that we can do generically, but for some functions, we can do this. In that case, we talk about direct sampling, and all my samples are completely uncorrelated. So let's see some examples. There's many, but I took some. Well, one, a very simple one, is what we call tower sampling. The idea is I want to draw n numbers. So I want to draw numbers between 1 and 10, say. And I want that the number 1 appears with probability pi1, say 0.2, that the number 2 appears with probability 0.3, number 4 with probability 0.15, and so on. Okay? So that's what I want. Okay? So how can I do this? Starting from my random number generator. Well, I can show you this with a drawing. Why it's called tower sampling. So I'll just do it with 3 numbers to make things simple. So that's the probability pi that I want to get, pi k. And I basically have 3 possibilities. So that's the probability for number 1. Probability for number 2, say something like this. And probability for number 3. So sorry, that was 2. Say 3. I want to draw these numbers 1, 2, 3, 1 with this probability, 2 with this probability, 3 with this probability. The sum of those lengths has to be equal to 1. Okay? So how do I do this? Well, I turn this into a tower. So I transform this into a tower where I put the first block like so, second on top of it, and last one. This, okay? This goes from 0 to 1, okay? And I introduce the cumulative probability. So this is the probability here. This is my pi 1, pi 2, pi 3. And the cumulative probability is the sum of everything. So if I go from here to here, this is big pi 1, from here to here, pi 2, pi 3. And what I do is I throw a random number between 0 and 1, and I just see where it falls. If it falls in this column, I say it's number 3. If it falls here, it's number 2. If it falls here, it's number 1. Okay? And quite clearly, just because of the area of the different places, well, this will draw with the right probability. Okay? So that's the idea. You see that's a tower. This is why it's called tower sampling. And maybe just to make this written in mathematics, so I start from my probabilities. I construct this cumulative distribution, which is the sum of the probabilities from 0 up to L. I draw a random number mu, and I identify between which 2 cumulative probabilities this falls. This basically tells me in which block I'm falling. Okay? Then I find k, and then k is the number I'm sampling. So that's quite a simple code to implement. Imagine I have this function in Python. I give it a list of probabilities. I construct the cumulative sum, put this in big pi. I draw a random number mu between 0 and 1. And this loop identifies in which box I am. Okay? So this is linear in terms of computational cost. One can do better than this, but this is really just for the illustration. So you can try this function, take a certain number of samples, 2 to the 14, take a list of probabilities, and take all of those samples and do a histogram, and you get what you expect. The red dots are the target distribution, and the purple blocks are the histogram. I do indeed get my tower sampling. Okay. So, okay, that's very simple. There are actually lots of Python functions to do this. You don't need to code this yourself, but it's more of an illustration. So how can I do a continuous function now? So imagine I don't want to do a tower sampling of a discrete variable, but I really want to go to a discrete probability distribution pi of x. Well, I want to turn my original discrete probabilities into something continuous, and my k becomes a continuous variable x. Okay? So what was originally my cumulative distribution function is now the integral from minus infinity all the way to x of my target probability distribution. That's this function capital pi. I draw a number between 0 and 1, and identifying where it fell is really identifying now the value of x of my cumulative distribution function such that it gives you mu, the number that I drew. So I basically need to invert this. So to get and to produce samples x which are distributed according to the right probability, what I need to do is to draw mu's uniformly and then to take the inverse cumulative distribution function of that uniformly distributed number. Okay? So you see where the difficulty is. I mean, for some functions, I will be able to compute this integral analytically and invert it analytically. But if I'm not able to do this, well, this is not going to be a very solid method. I don't want to do a numerical integration every time, right? But for some functions, you can actually do this, okay? So let me take two examples. The first one is completely trivial. Let's say that I want to draw uniformly, but not between 0 and 1, but between a and b, okay? Well, then my probability distribution is 1 over b minus a, whenever x is between a and b. The cumulative distribution function, well, this time the integral is really easy to do, just x minus a divided by b minus a, okay? And I can invert it. I just get a plus b minus a times mu, okay? So the recipe to get my random numbers uniformly sampled between a and b, well, is to start from a and then to scale times b minus a, my random number between 0 and 1. This is a very intuitive function, but you see at least it shows that the formula works. Okay? Is that clear? Great. We can do this with something slightly more sophisticated. So let's imagine I take a probability distribution, which is now this decaying exponential. Okay? Well, again, I can do everything analytically in this case. I integrate the function. It's again an 1 minus the exponential. I can invert this. I get this minus 1 over lambda times the log of 1 minus the number that I'm drawing, and I have a recipe to draw x numbers according to this probability distribution here. Again, you can give it a try. Just take many samples, 2 to the 14, take a list. These are numbers that are sampled uniformly between 0 and 1. I take minus the log of this and divide by lambda, and you see I get the histogram, which is this purple histogram, which is, again, exactly what I'm expecting, which is the target distribution, this exponential. So for a certain number of functions, you can actually do this, whenever you can do the integral and the inverse analytically, this is probably the best way to generate samples because every single sample will directly be distributed according to the right distribution and is completely uncorrelated from anything else you've done. Okay? Any questions about this? But as you can guess, in most interesting cases, we will not be able to do this. This is just to get your standard distributions. Similar things can be done to get a Gaussian, to get a Laurentian distribution. I mean, Laurentian is maybe not the easiest one, but at least, there's techniques for this. But when we go to more sophisticated functions, of course, this strategy, especially in multiple dimensions, this will not be possible anymore. Okay? Great. So a different approach, which is much more generic, but which comes with a drawback, is to use Markov chain approaches. So Markov chains are chains where you draw samples with a memory of just your previous sample. So you take one sample and you generate a new one just from the knowledge of that sample that you have now. And you forget about anything further in the past. But there's a correlation definitely between the throw at step n plus 1 and the throw at step n. Those two are not independent. Okay? So this will introduce correlations in your samples, but you will see it gives us a way to be quite flexible in the sort of distribution functions that we can sample. All right? Great. So again, the principle is I want to construct a sequence of elements. So x1, you can think of it right now as a number, okay? But you can already start off thinking about this as the configuration of a physical system. Okay? For example, if we go a bit later to an Ising model. This X1, you can think of it as a certain configuration of spins in my Ising model. And then I generate a new one and a new one, and this is my Markov chain. And the Markov chain is entirely determined by the transition probability, Px going to y, which tells me how the element x plus 1, at step n plus 1, sorry, is generated from the element xn. Okay? So you basically, the probability to get xn plus 1, if you start from xn, is this p xn going to xn plus 1. Okay? That's the transition probability, and I will assume that my Markov chain is ergodic, namely that if I do enough steps, I can in principle go from any configuration, any number, to any other number. It doesn't need to be in one step, but at least there must be a chain of events that brings me from any number to any other number. Okay? I will suppose this in the following. All right? Is that okay? So the hope, and you can prove, and I won't prove it here, under fairly weak assumptions, you can show that creating this sequence of numbers will eventually go to a stationary probability distribution. Namely, at some point, if you wait long enough, the points that you're drawing, they'll be drawn according to a stationary probability distribution. Okay? So let's try to see if there's a condition and how this stationary probability distribution is related to this P transition probability. Okay? So let's imagine I'm at step xn, and I want to ask what is the probability at step n plus 1 to be in the number x? Well, basically, this is the sum of all possible values of y at the previous step, different from x, times the probability to be at that value y, multiplied by the probability to go from y to x. Right? I want to go here. Well, what's the probability? Well, it's the probability to start anywhere but here and to hop into this x value. That's the first term. And the second term is the possibility that I just stay where I was. I was already in x and I stay in x. Okay, that's the second term. Okay? Now this probability to remain in x, I want to write it as 1 minus the probability not to be in x. So it's really 1 minus the sum of doing everything but remaining in x. Okay? So I have this equation here, and if I assume that I reach a stationary distribution, this means that at some point my pi, my distribution function, will no longer depend on my step number in my Markov chain. Okay? So pi n plus 1 will be the same as pi n, and this is my stationary probability distribution pi of x. Again, there are some assumptions for this to happen, but they're not too strong. Okay? So if I take this and put all those pi's to be the same, I obtain this simple equation here, which you see relates and connects my stationary probability distribution to my transition probability. So it means this equation gives me a recipe which connects my target probability distribution, this is where I want to go, this pi of x, and this transition probability p. So all the game now, which may sound simple, is to say, okay, I want to sample numbers according to pi of x. Now all I need to do, in principle, is find a transition probability p that satisfies this previous equation. And that equation is a very important one. It's called the balance condition, or sometimes the global balance condition. So whenever you find a transition probability p that satisfies for all values of x this balance condition, you're guaranteed, if the Markov chain goes to a stationary probability distribution, that it goes where you want. Okay? But it's you see, it's not a trivial equation. It's not entirely obvious when I look at this, how will I find this transition probability? So most of the algorithms on the market, they don't necessarily try to find p's that obey the global balance condition, but they actually try to satisfy a stronger condition, which is sufficient but not necessary, which is the detailed balance condition, which is just a condition for all specific values of y. So it imposes that those two things are the same for all values of x and y. Okay? So that's the detailed balance condition, and most of the common algorithms, and also the one that I'll be discussing in a minute, the Metropolis algorithm, is an algorithm that tries to satisfy the detailed balance condition. Okay? So again, this is simpler, but it's still not easy. We need a recipe to try to find ways to find P, this transition probability, if I have a certain pi of x, a target pi of x in mind. That's the game. All right?
You said that the detailed balance condition is sufficient.
Say it again, sir?
The detailed balance condition is still sufficient.
Yeah, so the detailed balance is more stringent. So it's definitely sufficient, but it's not necessary. So it means there are ways to find transition probabilities that do not satisfy the detailed balance, but they do satisfy the global balance condition, and those will be working as well.
So the detailed balance condition is basically for all of those y states.
Exactly. Well, the difference between the two is that the global balance only imposes that the condition is true for the sum over all y's, while the detailed balance imposes that it's true for every single choice of a y and x.
All y instead of any y.
It's for all y instead of the sum over all y. Yeah. So it's more stringent. Yes?
Probability distribution, it has like two variables, x and y. Does it depend on both of them or only on one?
This must be true for both of them.
Okay, both of them, so it has, so this detail is...
But you see that it's sort of a mirror. But yes, it has to be true for both.
Okay.
Yes.
Does relaxing this detailed balance condition to the global balance condition in principle allow for any advantages, or is it just...
Well, okay, so yes, it's a very good question, and there are, actually, funnily enough, algorithms that only satisfy the global condition generally work better than the ones that need to satisfy the detailed balance, and you're actually right, there's also, and this is a full line of research, of algorithms which don't necessarily try to obey the global balance condition, but still go to distribution functions that are, but this, you know, it goes far beyond what I'll be discussing. We have an expert about this in Paris, which is Werner Kraut, who likes this very much. Other questions? So I'll introduce you to a fantastic game which is called the Pebble game, and which is something which is quite useful when you try to get some intuition about how to work with Markov chains. So the game is the following. You have a certain cell structure, here a 3x3 tile, or set of tiles, okay? And you have a pebble somewhere on one of the tiles. Let's say I put it on 0 in the beginning. And what I want to do is move that pebble with the condition that it can only move to a neighboring cell, okay? And what I want is find a rule such that after a very long time, and repeating my rule many, many times, my pebble has been exploring all the cells uniformly with a uniform probability distribution. That seems quite trivial as a problem, but you see there's different ways to do this. For example, if my pebble is in the middle here, well, it's tempting to say that it will jump to one of the neighbors with probability 1/4, for example. But what do I do when I have a pebble here? Do I jump to one of the two neighbors with probability 1/2? Do you think this would give me a uniform distribution? Actually, no. This will not, as I will show in a second, satisfy the detailed balance. And this, if you do this, you'll be exploring the cells, but not with a uniform distribution. So you need to be careful, and you need to satisfy the detailed balance. So in that case, the detailed balance is very simple, because my probability is the same for all cells. So in this equation, all these pi's are the same. So I'm just left with the transition probability x going to y being the same as the opposite one. Okay? So I just want an algorithm, a strategy, that tells me that the way to go from x to y is the same as going backwards. Well, in that case, there's in principle different choices to do this, but if I start from 1/4, say starting from here and say probability 1/4 to go to a neighbor, well, I need to ensure I have the same probability to go from 1 to 0 than to 0 from 1, so it should be 1/4 for everyone. This means that if I'm here sitting in the angle, if I have probability 1/4 to jump here, 1/4 to jump here, well, there's a remaining probability 1/2 not to move. And I need to take this into account. And this is the only way to actually get to the uniform distribution. Okay? So you can code this. I won't maybe go into the code. The code is basically long only because you need to figure the neighbors of certain sites. But other than that, the algorithm is completely trivial. You just jump with probability 1/4 to one of your neighbors. And if you play the pebble game enough and look at what is your probability to stay on a certain cell, please go have a look at the code and play with it. You'll get a uniform distribution. But change one of those probabilities just a little bit, and you'll see you won't get the right probability distribution. Okay? So do you think if I try to generalize the pebble game and have a non-uniform distribution, like having one probability for even numbers and another probability for odd numbers. Do you think this is easy to do? This is a very small modification of the pebble game. Do you see a way to do this easily? It is non-trivial. So here the system is small enough that I can write my set of equations, because this is really a coupled set of equations. And so for this small system, I could actually write the full bunch of set of equations and try to solve it and find a probability. But if the system becomes large enough, this is going to become very, very painful. So even to do this very small modification of the pebble game, we will have to think about different algorithms to actually do this. There was a question, I think. Was no longer, yes?
I was going to ask you to put a boundary condition, is the same thing?
If you put a boundary condition, everything becomes easier, because then every side is the same as other ones, and then you can just jump to a neighbor with, say, probability 1/4, and then it's uniform. But in this game, to make it more interesting, there's no periodic boundary conditions. But you're right, in that case, it would be easier. Just move randomly. Other questions?
So when this algorithm is actually used?
This one?
Yeah.
Oh, no, I mean, this is not a very deep physics problem here. But so here what I'm trying to show is just that we need to impose the detailed balance condition in order to reach our target distribution. So that's the illustration here. In order to go to a strategy to get a non-uniform distribution over the pebble game, we will have to go to a new algorithm, which is the topic of the next chapter. Yes?
The detailed balance, as we posted, if we say that for every hopping we want it to be 1/4, would impose that globally between every two sides we would require the same one. But could I not just make this also dependent on
Sure.
neighbors?
Sure. Oh, yeah. Of course. There are multiple solutions, indeed. So, indeed, you're perfectly right. As long as the probability to go from 0 to 1 is the same as going from 1 to 0, and in that case, I could, for example, choose 1/3, it also works. So it doesn't need to be 1/4 everywhere. So this is just one solution. And actually, you're raising a good point. The final standard deviation that you get will very much depend on what strategy you use, and you'd actually be better off with what you're saying. So in that case, you want to maximize the motion of your pebble, and so this 1/4 would not necessarily be the best strategy. So yeah, very good point.
Does this global balance guarantee ergodicity?
So the moment your detailed balance is satisfied, automatically the global one is satisfied as well. So now finding an algorithm here that would only satisfy the global balance but not the detailed one, I'm not sure I have one in mind. I suppose you can cook up something, but yeah.
Like the ergodicity, so it is guarantee of ergodicity.
Oh, ergodicity, sorry.
Yeah.
Was that your question? Yeah, so you need to make sure you're ergodic. So in that context, this means that you need to make sure that with a finite number of moves, the pebble can go from any cell to any other cell. But it doesn't need to be in one move. So it's completely okay that you go from 0 to 8 in several moves, but you need to be able to go from anywhere to anywhere else.
Yeah, and satisfying the global balance.
And satisfy the global balance. These are the two conditions.
Are they independent?
Those are two independent conditions, yes. So yes, indeed, you're right. So it's not enough to satisfy the global balance. If you're not ergodic, this is not going to work. So you need to be both ergodic and satisfy the global balance condition. That's right.
Is there a way of like estimating, or we assume that it's ergodicity? So
Oh no, there's no way to, I mean, you need to check yourself and make sure that whatever is going to be your algorithm, that it is ergodic. There's no way, actually it's a very vicious problem. If you run a simulation and made an ergodicity problem in it, you will not see it easily. It will give you slightly wrong results or sometimes very wrong results, but there will be no way to easily tell. So you need to think long enough, and we've been running in those kind of problems in the past. It can be a very delicate thing. So you need to think and make sure it is ergodic, yes. Other questions? Very good, so maybe a quick summary. So we've been discussing Markov chain methods. One of the big difference with respect to the direct sampling methods is that now my samples are correlated, which means that the sample that are generated at a certain step, well, will know about the history of what has happened in the past. And so the numbers that I get are correlated, and this means that I will need to be careful when I do estimate the error bar on my result. If there's very, very strong correlations between my samples, this 1 over square root of n is not correct. I need to correct this with the autocorrelation time. I'll come back to this, but this is something you need to keep in mind. And very much, the job that we have when we design algorithm is very much about finding ways to reduce this autocorrelation time the most we can, okay? All right? So now we'll discuss ways to find generically these transition probabilities P. There's many different algorithms, which are names which maybe you've heard before, like Glauber, Wolf in the case of the Ising model, the heat-bath algorithm. But I will really just focus on one, which is maybe used the most, which is called the Metropolis-Hastings algorithm, which is one way to satisfy the detailed balance with a proper choice of this transition probability. Okay? Great. So this is the important part, I think. This is where I really want to get in terms of equations and concepts, and then we'll actually just apply them for the two-dimensional Ising model, okay? So this is a good time to ask questions if you have some. So the Metropolis-Hastings algorithm is a rejection-based algorithm. So it's based on the principle of accepting, rejecting some proposals. So what does that mean? So that means that I will decompose my transition probability, P, and cut it into a proposal, and then either an acceptance or rejection of this proposal. So it means that when I move, I start from a certain configuration or a certain number X, I propose a new number, new configuration Y, and I am entirely free to choose how to do that. Total freedom, with the exception that I need to ensure that this is going to be ergodic, okay? But except for that restriction, this proposal probability can be anything. So it can be move the pebble to the neighbor, move it somewhere else, take a mirror, take whatever you want. This is your proposal. Okay? You're free to do this. But then, this move that you propose, you have to accept it according to a well-defined acceptance probability, which is given by the Metropolis-Hastings algorithm, and which tells you, okay, accept this proposal with this probability, which is a ratio which involves a ratio of the new probability at the new position, at the probability distribution at Y, divided by the current probability distribution. So you sort of see that the larger the probability distribution of the new configuration, the more likely you are going to accept it. And it also involves a ratio of the transition of the proposal, T, from going to that configuration. Okay, so it's a ratio again of both. Okay? So it's very unfortunate because the transition probability is called P, and the proposal is called T. So that's very bad, but unfortunately that's the convention in this field. Sorry about that, okay? Great. So let me show you quite quickly, but take the time to go back to this slide, that this indeed satisfies the detailed balance condition. Again, the detailed balance condition is this here, right? And now the Metropolis Hastings says that this transition probability should be replaced by a proposal times an acceptance with a specific formula for the acceptance. So now I'll make the assumption that the numerator is larger than the denominator, is smaller, sorry, than the denominator. In that case, the minimum is that ratio. So this acceptance rate is this ratio here. You see many things simplified. This probability here cancels with this cancels with this. I'm just left with probability distribution y times this transition here, okay? But on the other hand, if this ratio was smaller than 1, it means that the opposite ratio was larger than 1, okay? Which means that this 1 here is the acceptance ratio of the opposite move, right? Which necessarily has, I mean, if this was smaller than 1, the opposite one, this number would be larger than 1, and in that case, the minimum would be 1. Okay, so this 1 here has to be the acceptance ratio for the opposite move. And you see that this here is, again, according to Metropolis Hastings, my transition probability. And I've actually shown that I satisfy the detailed balance. Okay? Obviously, you can get the same thing if you assume the opposite for the ratio. Okay, take the time to go through this, but you know, it works. Okay? So we have a recipe, and we can actually try this with our non-uniform pebble game now. Okay? So again, I have my 3x3 tiling, and I want to just say, okay, my probability is one number if I'm on even cells, and it's another number if it's on another cell. So what can I choose as a transition probability? Again, you're completely free to choose, okay? So one natural choice for my pebble is to say, okay, I move to a neighbor with probability 1, the number of my neighbors. Okay, that's a transition probability that you can choose, and it's defined like so. And then I just accept or reject the move with this acceptance rate. So to make things clear, if I make a proposal and I accept the proposal, well, I just put the pebble where I proposed. If I reject it, it means I keep the pebble where it is. And that's my next configuration in the Markov chain. So sometimes in the Markov chain, if you reject many proposals, you will stay in the same configuration for some time, and then you will move. Okay? Great. So again, you can go to the code and try this non-uniform pebble game with just 2 values for the probability distribution. Okay, that's just a check that it's normalized, not very interesting. Here, I won't go through the code. Actually, most of the difficulty is just to construct the table of neighbors. So to say, okay, if I'm in cell 4, what are my neighbors and how many do I have? That's the most painful thing to do. So that's most of the code here actually does this. It just constructs this table of neighbors. But once you have this table of neighbors, the algorithm is really very simple. You generate a certain number of samples. So I start with my pebble at position k equal to 0. Okay? Then I propose a new k. So for this, I just randomly choose, with uniform probability, one of my neighbors. Neighbors k here is a table of my neighbors. So this thing here just picks one of the neighbors with equal probability. That's my choice for this proposal of a new position for the pebble. Okay? Then I need to compute whatever goes into the acceptance probability, namely what is the probability to move from x to y. So this is just 1 over the neighbors of where I'm sitting now. I need to compute the opposite transition probability, which is 1 over the number of neighbors of where I will be in the future. Okay? And then I need to just know the probability, the value of the probability at the new position divided by the probability at the position where I'm staying now. And this ratio here is my Metropolis Hastings ratio. That's my acceptance probability. Okay? Now, the way to implement the notion of accepting with probability A, or with probability accept prob, Well, it's very simple. You just generate a random number between 0 and 1. And if this number is smaller than acceptance probability, well, then you accept the move. Okay? And you see that this way you only accept with the probability, which is this. And you even get rid of this minimum of 1 and the other one, because if acceptance probability is larger than 1, you are sure that if you draw something between 0 and 1, it's automatically accepted. So you sort of implement automatically this min as well. Okay? So that's how we do it all the time. All right? Well, run this for many samples, and this is what you get. Your Pebble game will indeed be sampling your different cells with this non-uniform probability. And this is very generic. So actually this code, you can also, it doesn't need to be one value for even and odd. It can also be anything, and this will just work fine. All right? Any questions? So who was already familiar with this? I fear that most of you are. Olivier? Oh, man. Okay, so a fair fraction of you know this very well. So you see the game. So where is the game? I mean, how, according to you, what happens if I choose different proposal probabilities? How will that change my algorithm in terms of efficiency? Why is it sometimes good? Why is it bad? What's your feeling? Oh, always accept would be cool, but I'm not choosing. The acceptance rate is imposed. But you're getting there, yes. Definitely, the best algorithms are those that are going to accept all the time. Are you sure?
They're going to accept the probability of our initial function when we integrate.
Well, so what do you want to do? It's sort of a trade-off, right? Imagine... Let's turn our Pebble game into a slightly more interesting problem, which is, well, it's not more interesting, but it's different. It's the continuous version of it. Imagine I have a square, I have a Pebble, and now I want to move it uniformly on the square, okay? So what do I want if I want to efficiently sample uniformly my distribution? Do I want to make super big moves? No, because I may get out of the square. Not good. Do I want to make super tiny moves? Not good, okay, because I'm not sampling efficiently the distribution. So there's always a trade-off when you do metropolis Hastings algorithms between having algorithms that have very large acceptance rates, this is what you're suggesting, but generally their drawback is that you almost don't move in phase space. So in that case, for example, if I just move a tiny bit my configuration, well, okay, I'm likely to accept it, but I have almost not changed my configuration. It will take a long time before I get to a configuration which is uncorrelated from this one. On the other hand, if I draw uncorrelated samples at random, well, most likely my acceptance rate will reject it because, it's very unlikely that I get to a good configuration with a high probability if you just go random. So the whole art of doing Monte Carlo is to find the correct trade-off between finding moves that make you move quickly in phase space and at the same time are not rejected ridiculously often, okay? And clever algorithm, there are some which get you everything. So like this Wolf cluster algorithm changes configurations a lot in the Ising model, but at the same time is accepted all the time. So there are beautiful algorithms that get you everything for free, but most of the time this is difficult. Does it make sense? Okay? Questions? Sweet. Well, let's try to apply this now to something real. Okay, the Pebble game is nice, but I also want to do a bit of physics, so let's go to the T-dimensional Ising model. I hope you all know it very well. That's the energy for a certain spin configuration. So on every side, a spin can have value +1, -1. There's both the ferromagnetic and anti-ferromagnetic Ising model. I'll be focusing on situation where J is positive, namely the system has a tendency to be willing to put spins in the same direction. Okay? So this system can be solved exactly in 2 dimensions. That's the Onzaga solution. We know it has a phase transition at a finite temperature. Above that temperature, the system is disordered. Below that temperature, the system orders all the spins align. Okay? Great. So what we want to compute in practice, to compute a physical observable, is something like this. It's my 1 divided by the partition function times the sum over all possible instances of my spin configurations times the Boltzmann weight, e to the minus beta, the energy of this configuration sigma, times the value of my observable for that specific configuration. That's what I want to compute. That's what's difficult. This is a sum over 2 to the power n terms. Okay? So let me write this more explicitly. So I wrote the partition function explicitly like so. When you look at this, now we have to decide, okay, I have found a strategy with Metropolis Hastings to, in principle, sample any probability distribution. So what would be a clever probability distribution to sort of try to evaluate these observables? The exponential, huh? The Boltzmann probability seems a very natural choice. It's almost a physically natural choice in the sense that, well, this tells you how the system itself sort of wants to go to certain configurations. The one that have too large energies are unlikely. So ideally, I would want to generate stochastically Ising spin configurations that appear with probability, the Boltzmann weight, e to the minus beta, the energy of that spin configuration divided by the partition function. Okay? Well, it looks like bad news because I have this partition function here, which is something that I don't know. I can certainly compute this, but to get the partition function, I will have to sum over everything. But this is where we're getting lucky with statistical physics because we actually have to compute a ratio. Okay? So if I feed this expression here, the partition function appears both on the numerator and denominator. It cancels out. And I can evaluate my physical observable by using this probability distribution pi and accumulate and measure my physical observable. The partition function disappears. Okay? So what I need to do is create a Markov chain which generates spin configurations according to the Boltzmann weight, and then measure on my Markov chain my energy, my magnetization, and normalize this by the sum of 1 here, which is just how many configurations I've been generating. Okay? All right? Makes sense so far? So, again, we're free to choose, if we do Metropolis Hastings, we're free to choose our proposal of a new configuration starting from a certain configuration. So imagine I have a spin configuration. What could be a way to propose a new configuration? It's written there, but let me hide it. What could I do? Flip a spin at random, right? That seems to be the most natural choice, and this actually works. We can discuss how well, but it works. So the transition probability would be, or the proposal probability would be pick a spin and flip it. That's my new configuration. Okay? Then the acceptance probability is, again, the minimum between. So this time, the transition probability to go from the first configuration to the one with the flipped spin is the same as going the opposite way. So in the Metropolis Hastings ratio, there's only the probability that appears. And the probability is the ratio of two exponentials with the energy. Okay? So it's only exponential to minus beta, the energy difference. And we get lucky when we flip a single spin, because when we flip a single spin, all the links of the Ising model have the same energy, except for the 4 links that involve the spin that I've flipped. Okay? So computing the new energy is actually very easy. I only need to investigate how much the link energies of my 4 neighbors will change. So that's very quick. That's nice. It means I don't need to sum over my entire system. I just look at how my local energy, if you want, my molecular field changed as I flipped the spin. Okay? And that's it. You compute this exponential, accept or reject your proposal with this. So in the practical implementation, how do you do? So you initialize your simulation. So you start either from a random configuration of spins or all spins aligned. I mean, you choose. And then you start proposing updates. You compute all the relevant variables that enter the Metropolis Hastings acceptance ratio, so the probability distribution at the new configuration, and so on and so forth, the energy difference. And then you either accept or reject your configuration. And then When you've done this, you've created a new configuration, and you measure, for example, the energy, the magnetization, whatever you're interested in, and you move on like this. Very important point. Even when you reject a move, you have to consider this as a new configuration in your Markov chain. Okay? One mistake that we see a lot with people that start doing metropolis hashings is that they measure only when they accepted a move. This is biasing your probability distribution. Okay? You need to consider the fact that if you stay in the same configuration, even for a long time, those are new instances of your configuration, and you need to take those into account. Okay? Any questions? Well, so you'll see it's actually very simple. So we'll actually go through the entire code simulating this Ising model here. So the beginning is just initializing your system. So for me, I just chose to write this as a table of -1 or +1 to describe spin +1, -1. And I put this in a two-dimensional array of size L by L. Okay, and I do this randomly. This is how I initialize my first configuration. Okay? Then the main thing is the Monte Carlo step. So how does the Monte Carlo step work? So forget about this extra loop here. What we first do is we pick two numbers KL, which are the coordinates of a spin in my system. So I just choose two random numbers between 0 and L-1. Okay? That identifies a spin somewhere. And then I compute the energy difference between the old and the new configuration. And as you can imagine, this involves the value of the spin that I'm flipping and the value of the spin at the neighboring sites. This means 4 neighbors. Okay? So this is exactly what this term is doing. It's looking at how the link energy is changing for the 4 neighbors of the spin that I'm flipping. That's my energy difference. Then my metropolis hashings acceptance probability is just exponential of minus beta this energy difference. That's what it is here. And again, I accept the move by just drawing a random number between 0 and 1 and checking whether it's smaller than this probability, acceptance probability. Okay? And if so, I flip the spin. If not, I leave the spin unchanged. Okay? Now you see, I'll be flipping one spin at a time if I do this. So it's conventional in the Ising model to consider that a Monte Carlo step is doing this L squared times. So I do this n times, for as many times as I have spins, so that I at least create new configurations which look a bit different from one step to the other. Okay, that's just a convention, and this is this extra loop. This is a convention. It does not mean that I will be flipping every spin. Okay, it's just that I do this enough times that my new configuration looks a bit different from the previous one. Okay, and that's my Monte Carlo step. Okay, so let's see in practice how things change at different temperatures. Again, this is the entire code. So I do this for 2 different temperatures. Okay, here this is beta is the inverse temperature. Okay, so here this line is high temperature, below it's lower temperature, just a bit below the critical temperature from Onzager. And all I've been doing here is starting from a random configuration and I've been doing 5 Monte Carlo steps between snapshots. Okay? So you see at high temperature, I start from a random configuration like this, and the new configurations I create, well, first are quite uncorrelated, so they don't look the same. Well, they all look the same in a sense that they all look disordered, but they're actually quite different. But you see I'm at high temperature, my configurations are typically disordered. At low temperature, well, quite quickly, the configurations that have the highest Boltzmann weight are those that have aligned spin, and you start seeing the formation of islands of spins that go in the same direction, which is exactly the physics that you're expecting in the Ising model. But you do also see at the same time that those configurations, they start to look very much the same. So at low temperatures, what we typically start to see here is an ergodicity problem. I am not moving very quickly in my phase space. My configurations only change little, and I will have to run long simulations before I go through all the characteristic configurations of my system. Yes?
If I have these large structures with these grain boundaries, something more cleverly than just trying to flip every.
Yes. So because so this is a well-known problem, and so what's happening as you get close to the critical temperature, the autocorrelation time, so if you want the time it takes to disentangle configurations becomes longer and longer. Okay? So in this algorithm which flips a single spin, there is no way to get around this. You get this critical slowdown if you want. So there are much more clever algorithms, and one which is especially clever is the Wolf algorithm, and what it does is it sort of identifies, it's the spirit, it doesn't really exactly go like this, but it identifies islands of spins that go in the same direction and flips all of them at the same time. So it basically flips an entire island like this together. It has a high chance to be accepted because the energy difference is fairly small. It's only the boundary energy. So it's actually accepted with quite a high probability. And at the same time, it changes the configuration a lot. Okay? So it's slightly more subtle than what I'm saying, but that's basically the spirit. Yeah? So how do I compute observables? Well, it's very simple. I just need two functions that compute, for example, an energy of a configuration if I have one. So that's just looping over all spins, checking the neighbors, and computing the link energies. You can compute magnetization. This one is even simpler because it's just the sum of the value of the spins everywhere. Okay? And then my Monte Carlo simulation would look something like this. You do a loop over many, many Monte Carlo samples. You do a Monte Carlo step. So a Monte Carlo step will create a new configuration. And you just accumulate in a table the energy of those new configurations. Okay? And then you look over time how this evolves. So for example, if I do a simulation here for 1,000 steps, well, the energy is this purple curve. And to get my physical value, well, I just average this over time. Okay? So this red line is the running average. And you see after a certain number of configurations, it stabilizes, and it gives me an estimate of the average energy of my system. Same here for the magnetization. So I can run that for different temperatures. Again, this is the entire code. So you loop over a bunch of temperatures and accumulate energies, and then just plot the averages. Okay? And you see something like this, which is what you expect. So at high temperature, these are the red lines. The energy is higher. As you cool down, as expected, the average energy goes down. The magnetization instead, at large temperature, is close to 0. This is my disordered system. As I go below the transition temperature, the system starts to order, and the magnetization gets closer and closer to 1. Okay? You can also put this on a plot, magnetization versus temperature. And you'd get something like this at high temperature. This is a small system. It's 8 by 8. Now you cannot see a true phase transition, but you see tendencies. So you see at large temperatures, the magnetization gets closer to 0. And as you go through this value, this is the Onsager value, but for an infinite system, the magnetization shoots up and goes to a larger value. The system gets ordered. Okay? So you see, with very simple codes, you can actually address a fairly difficult problem. Yes? Oh, okay, so this is actually over a fairly short time. Here I've only been making something like 5 steps. If you run this longer, eventually you'll be left with only a couple of small islands that appear and disappear. Yes. Okay?
And also you had the word danger there, what does it mean?
Yes, so yeah, exactly. So that's the last topic, and I see I'm running out of time, but I'll convey that message a bit. So I've been trying to put error bars naively on this plot. So to compute error bars, if I'm naive and I suppose that all my samples are uncorrelated, the standard deviation would just be take my samples, I take the standard deviation of this, and I divide by square root of n. Okay? This is wrong. It's wrong because my samples are correlated, and you can see it with your eyes that it's wrong because the error bars are almost, invisible here. And definitely, you can see just from the shape of the curve that here you expect, for example, to have larger error bars to have something which makes sense. Okay? So this was just an illustration to show you that don't be naive, don't compute error bars by just doing 1 over square root of n. You need to take into account the fact that your samples are correlated. That's the topic of the next chapter, which I will unfortunately have to go quickly through, but I will still tell you a bit about this. Questions so far? It's pretty cool, huh? It's really, really simple, and you can already do cool physics with that. All right? All right. So let's indeed address the error bar analysis. This is a delicate point, which is often not done well enough, is how to properly compute your statistical error bars. Okay, you need to be careful with the fact that the samples that you generate are correlated. You cannot consider that they're completely independent, and so you cannot just divide by 1 over square root the number of samples you have. You need to correct for the autocorrelation time, so the time it takes to create 2 independent samples in practice. Okay? So this, I'll let you go through the beginning. It's probably useful. It tells you how you can get estimates from your samples of the variance in your system. But I think it's more important to discuss the notion of autocorrelation time. So let me illustrate this. So if I run a Monte Carlo simulation and compute the energy, if you look at it from, for a very large number of steps, it looks like this is, oscillating a lot. But if you zoom in a bit, what you see is that your energy, it takes quite a bit of time. You see there's a lot of autocorrelation. So if I go from here, it's quite clear that the bunch of configurations that are here are all still quite connected to the one that I had before. Okay? So there's visible autocorrelation time here. So how do I, in practice, compute this autocorrelation time? How do I correct for the fact that my samples are correlated? So there's different strategies. Again, I won't have really time to go into the details, but I think it's important that you know them, and then you'll have more time to learn about them. One of them is to actually try and compute the autocorrelation function, which is a function which measures how much a configuration is correlated to a configuration at a later time. Okay? So how do we even, define the autocorrelation time? So the autocorrelation time for me is how much, if I take the correct standard deviation, or that's actually the variance, sorry, the correct variance, and compare it with the naive variance, which would be the one that supposes that all the samples are uncorrelated, the ratio between those two, so if you want the error that I'm making, is by definition twice the autocorrelation time. So if you want this autocorrelation time up to a factor 2, is basically if you want how many samples you need before you reach 2 independent samples. Okay, that's sort of a way to think about it. Okay. So for the specific example that I was looking at here, I can try to compute the actual error bar, and to do this, I just run completely independent Monte Carlo simulations 40 times and measure the energy. Okay. If I run completely independent simulations, they're indeed independent, and I can just use my standard formula and get an actual error bar for this. If I compare this with the naive autocorrelation that I get from a single simulation where I would be dividing by 1 over square root the number of samples, well, what I would get is this estimate of the error bar, which is 10 times too small. Okay? So you see that in practice, I have an autocorrelation time in the system which is as large as 160. And it's not crazy. If I look at this, well, it does certainly take about 200, 300 steps to really decorrelate my samples. Okay? So now this is not very practical. I mean, if for every simulation, a way to get an estimate is to basically redo many, many independent Monte Carlo simulations, this is not very efficient. So a different way to approach the problem is to compute the autocorrelation function, A of k, which is an autocorrelation function. So it computes the average of my configuration at time L times the configuration at times L plus k, takes the average of this and removes, if you want, the disconnected part of this. Okay? If the samples were completely uncorrelated, this autocorrelation function would be 0, because this, if those two samples at different times were completely uncorrelated, this would be the product of two averages, would cancel with this, and I would get 0. Okay? If instead they are strongly correlated, well, this autocorrelation function takes a finite value. So when you plot it, it typically looks like this. So the autocorrelation function, if you compute it numerically from your data, well, it's a function that by construction and definition starts at 1 and then decays. And basically, you can read your autocorrelation time by seeing it decays exponentially, and the factor in the exponential is basically the autocorrelation time. So from this, you can read, even by just looking at it, you can see that 200 is more or less the decay rate here, the decay time for your exponential. Okay? One way to get it more mathematically, and you can prove that this is the right way to do it, is to take your autocorrelation function, sum it, and add 1/2, and this gets you this factor and the autocorrelation time. So this is one way to get your autocorrelation time. Once you have the autocorrelation time, you take your standard formula 1/√n, okay? But you multiply this by your autocorrelation time to compensate for the fact that you only have uncorrelated samples after tau steps, okay? So that's one approach. And you see if you correct this, so the actual error bar is this 0.018. If you correct by using this using the autocorrelation time from the autocorrelation function, you see that now your estimate of the error bar is much more reliable and actually very close to the correct one. Okay? That's one way. Computing these autocorrelation functions may be a bit cumbersome. So a different way is something called the binning analysis. So what you do is you take all of your data, you put it in a long list. You compute the naive, standard deviation for this bunch of data. Okay, so you take all of your data and compute the standard deviation by taking 1/√, everything. Okay, this is going to be a too small estimate of your error bar. Then you take your long list and take pairwise bins next to each other and create a list which is now twice shorter and where every entry is the average of 2 entries of the first one. So I sort of bin it, and it becomes twice shorter. You sort of realize by doing this that probably now between 2 bins, well, they're more uncorrelated than before. For this new list, again, compute the naive error bar. And do that again as you divide by 2 by 2 by 2. Okay? When you do this, you observe something like this. So you have your original estimate of the error bar, the naive estimate, which is way too small. And as you bin, the system becomes more uncorrelated, but the error bar becomes more realistic. It increases. And what you see if your system, your list is large enough, is that eventually this plateaus to a value which is the correct estimate of the error bar. Okay? Now, as you do this more and more, eventually, because you divide by 2 every time, you end up with a list which has 4 numbers, and obviously, getting a serious estimate out of 4 numbers becomes wrong, and this is why this eventually starts going ballistic, okay? So, you need to reach that plateau. So that's a different way to do it, okay? But you see, those are faithful ways to actually get a correct error bar. All right? Great. Maybe last thing that I want to mention, and again, I won't go into details. Please, take the time to read more about this if you're facing this situation. Is those are cases in which what I was sampling was directly the physical quantity that I was interested in. But sometimes we want to compute, a specific heat or something, or a Binder cumulant, which is the ratio or which is a nonlinear function of several averages that you've been computing. And the question is, how do I compute the error bar on those? Because I am not directly measuring these guys. I first measure average values, for example, the average value of the magnetization to the power 4, and then independently the average value of the magnetization squared. And out of this, I compute the Binder cumulant. But then how do I get the error bar for this guy? So in principle, one can do the proper error bar propagation, because I have a formula here. I eventually know the error bar on this guy, so in principle I can do all the math and get to the error bar of this. But it can become cumbersome if you have a very complicated nonlinear function of your averages. So one way to make this more automatic and more systematic is to use something which is called a jackknife analysis, and in a certain sense it will remind you a bit of the binning analysis. So what you do is you take your entire set of data and you cut it into, say, 20 bins. Not too many, like 20. Okay? And then in each of these bins, which is quite long and has quite a bit of statistics, you compute the value of the thing you're interested in. So for example, your Binder cumulant or your specific heat. Okay? So this will be your jackknife estimate in that specific bin. So that's this AJ here with an index J which runs from 1 to 20. Okay? Clearly, if I take the average of these guys, I get my average value. This is what I'm looking for. That's very easy. It's just the average of the averages. No problem. This is the average value I'm looking for. But I can, from that, compute the error bar by taking this formula here. Okay? So this is basically taking your variance of your 20 bins, fixing it with a clever prefactor that you need to work out if you read more about Jackknife. Take the square root of that, and this will give you a fairly good approximation of, or a good estimate, I mean, of the standard deviation of more sophisticated averages. Okay? Again, here the goal is not to go through everything. It actually takes a bit of time to derive this all correctly, but I just want to tell you that those things exist, and then you can take time to read more about this. Actually, in the last notebook references, I've put, where is it? This link here, which I think is very nice, it's only an archive paper by Jung here, but which really goes into all of this quite in the details, and it's very clear. So if you want to learn more about careful error bar analysis, you'll find it there. I think it's a really good reference. There's another one which is also nice here by Troyer and Omega Okar, which is also quite nice and discusses this in the details. Okay? Well, that's pretty much all I wanted to say. Those methods we'll put in practice tomorrow in the context of DMFT, so we'll see how stochastic methods can be now used, not for the Ising model, but rather to actually try to solve quantum impurity models. Do you have any questions? Well, if not, you know where lunch is.